Hello everyone, and today I'm going to introduce the term project, which is about filter approximate nearest neighbor search, or filter ANN. And here are the two main references for this project. And these papers provide the background and motivation for filter vector search and help us understand the design space of filter ANNS method. And here's the outline. So what is filter vector search? In filter vector search, we do not search over the entire database. Instead, we first apply some relational filters to restrict which data points are eligible for retrieval. For example, suppose you are looking for you are looking for papers on filter vector search. You type a keyword into Google Scholar, but the result may include older papers. So to narrow them down, you can set a date range to exclude those older papers. And this is one example of filter vector search in practice. So the search is based not only on vector similarity, but also on whether each data point satisfies the filter condition. And the main challenge in filter ANNS is that applying a filter changes both the size and the distribution of the searchable data point. Suppose we have many data points, a query, and its three nearest neighbors. And this is the typical setting in ANNS. But once we apply a filter, the set of searchable points becomes smaller, and the nearest neighbors may be very different from those in the original full dataset. And you can see the true neighbors are different after we apply a new filter. And the distribution may also change significantly. So ideally, a filter-aware index should behave as if it were built only on the data point that satisfy the filter. And this slide shows the same idea with a different filter. When we change the filter, the subset of qualified vector changes again, and the local neighborhood structure around the query also changes. This means that a standard ANN index built for the full dataset may not be well aligned with the filter search space. And that is why filter ANNS is more difficult than traditional ANN search. So how to solve this problem? The first baseline is pre-filtering. The idea is straightforward. We first apply the filter to the dataset and keep only the qualified vectors. And then we perform KN search on this filtered subset. And this gives us exact ground truth because the KN search is done directly on the correct candidate set. And however, it can be slow, especially when we have to re-rank all the qualified vectors. So the second baseline is post-filtering. And in this approach, we first apply ANN search on full dataset. And in this term project, we use And after retrieving the candidates, we then apply the filter and keep only those that satisfy the condition. And this is usually faster than pre-filtering because the ANNS search is efficient. But the downside is that many retrieved candidates may not survive the filter, which hurts the final retrieval quality. And this slide highlights the main weakness of post-filtering. The traditional ANNS method only care about vector similarity. So, so many retrieved candidates do not satisfy the filter. As a result, a large portion of the candidates was wasted. In this example, around 80% of them are discarded after filtering. And this means we spend computation on points that are not actually useful for the filter search task. So even if post-filtering is fast, its recall can become quite poor. So the better idea is inline filtering, also called joint filtering. Instead of separating filtering and vector search into two stages, we combine them into the same process. That means filtering is considered during both indexing and searching. In other words, the index is built with both vector information and attribute information, and the query is also transformed in a way that reflects both similarity and filter constraint. And this allows the search process to generate candidates that are more likely to be both. This allows the search process to generate candidates that are more likely to be both similar and filter compatible.
So it means you have two index structures, two index vectors and attributes. One for index your vectors, one and for index your attributes. You have two different index structures.
Maybe you can do it in that way, but in our next slide,
we will combine it together.
We can in this baseline we just concat two vector, but you can build two different index as well, maybe. Okay. And before introducing the filter augmented version, let me briefly review Euclidean LSH. In Euclidean LSH, we hash each vector using a random projection W plus an offset B, and then divide by an beam width R. And the intuition is that vectors that are close in Euclidean space are more likely to fall into the same hash bucket. And this makes approximate nearest neighbor search much faster because we only need to compare points in relevant buckets instead of scanning the entire data set. And now we extend standard LSH to filter augmented LSH. The key idea is to build an augmented vector denoted as x prime by concatenating two parts. The first part is the original vector scaled by alpha, and the second part is the attribute representation scaled by 1 minus alpha. And in this way, the hash function considers both the vector embedding and the filter-related label information. So similar vector with compatible attribute are more likely to be hashed together. And this is how we incorporate filtering directly into the ANN indexing framework. And note that the attribute representation is a k-dimensional vector where each element is the same label scalar. So in this figure, the k is 2.
So do we need to do some scaling? I mean, in your attributes, maybe the scalar in each dimension are different. So do you need to do scaling before it? Like the normalization.
Maybe you can remove scale, but just add some flexible. So you can also let k equal to d. The k can change. And then here we compare the candidate statistics with and without filter augmentation. And the key point is that filter augmented LSH produces fewer wasted candidates while achieving better retrieval quality. In particular, the average survival rate improves from 20% to 44%. And this means that a much larger portion of the retrieved candidates remains valid after filtering. As a result, the search becomes more efficient and better aligned with the actual goal of filter retrieval. And finally, we compare the overall performance. With filter augmentation, the method achieved higher recall while remaining 3.43 times faster than the prefilling baseline. And compare with prefilling, it preserves much of the efficiency advantage of ANN search while also improving filter retrieval quality. So this is exactly the trade-off we want in filter ANNS, which is a high recall and high throughput. Okay, and the dataset for this term project is SIFT dataset with random generated label. For dataset, we have 1 million 1 million vectors, and each with dimension 128. And for the test set, there are 10,000 queries, and again with 128 dimensional vectors. And each vector is assigned a label sampled from a normal distribution, and the label is stored as an integer in the range from 0 to 1,000. For each query, the filter is defined as a label range, where the normalized filter width is between 0.5% to 40%.
I don't understand. What is R and L? What is that? What are they?
R and L is your filter range. So R is right, L is left. And these two.
Oh, so your query will give a range.
Yeah.
In your query, you give a range, for example, like 200 to 300.
Yeah.
Like this. And the filter range. What do you mean filter range? Filter range is used for.
Filter range is the filter for this query. So, for example, if your filter range is 200 to 300, then the filtering is to remove the vector they are not in this range. And here is an example of how to use the code from the README file. And to run the shift experiment, you first set set out the environment, and then run Python main.py as a shift argument. And please make sure to include the shift argument. Otherwise, you will use the wrong dataset, which is randomly generated. And the file we will be working on is lsh underline index.py. And here we connect the mathematical formulation to the actual implementation in this file. The compute key function corresponds to the hash function, and the vex corresponds to the augmented vector x prime. And the first line computes the projection, which multiplies x by random matrix W and add a random offset B, which is here, this. In the second line, computes the hash key for x prime by dividing the projection by the beam width R, and then apply the floor function. And here is how we construct the augmented vector x prime for indexing. Each base vector is augmented. Each base vector is augmented using its label vector, where the label scalar is broadcast to a k-dimensional vector. And for searching, each query is augmented using the midpoint of its filter range, and which is also broadcast to a k-dimensional vector. And here is the baseline performance with the default configuration. And the table compares pre-filtering and inline filtering in terms of recall and QPS. And this is inline filtering. And as expected, pre-filtering gives very strong recall, which is exactly the ground truth. But it is much slower. And inline filtering is significantly faster, but its recall is much lower. So this result motivates the project. We want to design a better filter ANNS method that improves this trade-off. So finally, here is the term project requirement. Your task is to design an filtering ANNS method that maximizes the final score, which is defined as QPS divided by 100 and multiplied by recall squared. And in this formula, QPS stands for query per second, and R denotes recall at 50. And your goal is to get closer to this area. And the inline filtering baseline is here. And each group should consist of 2 students. And please submit your code before June 2nd, because we need to measure QPS. And for fair comparison, QPS must be measured on the same machine. So after I evaluate all group scores, I will announce the final result on equals 2. So please include your final score in your slides. Okay.
It's all.
Yeah.
Okay. Thank you, Leo. Shift F. Shift F.